Hello all, welcome to the talk. Today I will be presenting my thesis work on millimeter wave beam selection in time varying channels with orientation changes and mobility. My name is Ashok. Here is the outline of the talk. We first introduce the millimeter wave band, challenges with it, the need for beamforming and beam selection. Then we discuss the spatial channel model, which is the prominent channel model used for studying the millimeter wave systems. Then we propose a beam selection method with orientation changes. Then we extend the work using the latent Thompson sampling for beam selection. Then we conclude. One of the key new additions to 5G from 4G is the support of millimeter wave bands for cellular communications. Millimeter wave bands range from 30 gigahertz to 300 gigahertz, while 3GPP 5G supports the bands from 24 gigahertz to 52 gigahertz. When compared with the bands supported in 4G, these mmWave bands are at least 10 times higher. This results in excessive path loss. Excessive path loss results in insufficient link budget to complete the link between the transmitter and the receiver. For example, when we use the same transmit power that is used in 4G communications and use similar RF and antenna structures, we cannot reach the receiver to complete the link at millimeter wave bands. To overcome this problem, a new transmission method is adopted in 5G, which is called beamforming. Beamforming lets the transmitter to focus the transmitted signal in a specific narrow direction. To cover the whole region, the transmitter needs to form multiple directional beams. Similarly, beamforming at the receiver lets the receiver receive the signals from fixed narrow direction. Here too, to cover the whole region, receiver needs to form different directional beams. With these multiple beams that are possible at both the transmitter and the receiver, we will need the transmitter to know which direction to transmit and the receiver to know which direction to receive. This is a new problem to solve to efficiently use millimeter wave bands. On this slide, we introduce a simple measurement procedure that lets the base station and user equipment to find the direction to transmit in and the direction to receive in respectively. Here, the base station transmits the pilots from each of its transmit directional beams in a sequential fashion in a burst here. And such bursts are repeated periodically from the base station. While the receiver measures each of these bursts with one of its receive beam and in a sequential fashion over all of its receive beams. With this, we have measured the total number of beams corresponding to BS transmit beams, the BBS times the BBUE times number of beams are measured before we go and select a transmit and receive beam. So once it knows the transmit and receive beam pair, it reports this information to the base station. And base station uses this information to transmit the next data transmission in the downlink. Note that there are a lot of beam pair options to measure here, which corresponds to product of number of beams at the base station and the number of beams at the receiver. This takes a large amount of time, and during this time, UE orientation may change because of the user movements, or even user movement in lateral direction can also change the beam that is the best at current moment. Hence, the beam selection is sensitive to the UV orientation changes and the lateral mobility and time variations in the channel. On this slide, we provide a measurement procedure that aligns with 5G. So you observe that the data is interleaved between these multiple pilot bursts, right, these data slots. Each pilot burst, as we discussed in the previous slide, contains BBS beams and pilots corresponding to them. And such pilot bursts are repeated periodically. Each pilot burst is received by a UE receive beam, specific beam, and in a sequential fashion. The UE cycles around its own receive beams to measure all the transmit and receive beams. There are BUE beams possible at the UE. And we define a measurement cycle consisting of S measurement occasions, S pilot bursts, in which SUE beams are measured. Okay. The beam pair is selected at the end of each measurement cycle. At the end of each measurement cycle, we select the beam pair. The selected beam pair from the previous measurement cycle is used in the current measurement cycle for receiving the data. And there are n data slots, and these data slots are received by the beam pair that was selected in the previous measurement cycle. So an important question to ask here is, what should the transmit and receive beam be to maximize the average data rate in the next n slots? While making a decision at this point, we ask this question: what should the transmit and receive beam be to maximize the average data rate in the next n slots? So to understand it, we need to be able to characterize channel observed at the measurement occasions, and the channel at the data slots accurately. On this slide, we describe the spatial channel model that accurately models the time-varying millimeter wave channels. It has NTX antennas at the base station that are used to form BBS beams, and NRX antennas at the UE, which are used to form BUE beams. It models scatterers represented by cluster of rays and multiple such clusters representing the multiple scatterers. Here we have C clusters and L paths for each of these clusters. It models angle of departure, angle of arrival for each cluster, and angular spreads corresponding to them as well. It models line of sight and non-line of sight paths. It captures the user orientation changes and the lateral mobility as well in this model. The spatial channel model is adopted by 3GPP as a reference channel model for all its evaluations and is empirically validated extensively. And here the channel H represents the MIMO channel observed at the NRX antennas from the NTX antennas. On this slide, we have shown the channel correlation properties of SCM. Here on the left side, we plot power correlation coefficient rho BU of T, T plus tau that corresponds to the power correlation of channel gains at time T and T plus tau as a function of lag tau. Okay, here you observe that the channel power correlation can both be positive and also negative, and it oscillates between these two values. Okay. And the right side plot shows the level set contours of a joint PDF of beam pair gain at time T and T plus tau. This shows the level set contours of the joint PDF. So here if you see, the level set contours for the positively correlated case are here, where you see the correlation between channel gain at time T and T plus tau is positive as the channel gain at one time increases, another time also increases. And you also see other set of contours at different lag, which is plotted here. That shows the negative correlation. As the channel gain increases, the channel gain at t plus tau decreases. Okay. So this is observed at two different lags. That's what is plotted here. Okay. So channel exhibits both positive and negative power correlations, and there is no analytical characterization available in the literature for this kind of channels. So we propose a modified bivariate Nakagami M model that accurately models joint statistics of the channel gains seen at the times of measurement and data transmission. So this plays an important role in further design of our beam selection algorithms later in the presentation. So this model handles both positive and negative correlations that are possible in SEM, and ambient parameters are all expressed in terms of SEM settings that are known to us, and it's also analytically tractable. So this gives us a good handle to explore the problem of interest further. Okay. So here we quickly show the modified bivariate Nakagami M model for the positive correlation case. So it is similar to bivariate Nakagami that is there in literature, but you observe the parameters omega corresponds to mean channel gain at time t, and the rho corresponds to the power correlation coefficient at time t and t plus tau, and m corresponds to the Nakagami parameter. And here you see the omega bu of t, the mean channel power at time t, captures the varying mean power that is possible in these channels. For example, when a UE orientation changes from direction 1 to direction 2, the beam mean channel power in a particular for a particular beam changes. That represents a non-stationarity, and actually this is well captured in the this model. And for the negative power correlation case, where rho is less than 0, we have very similar representation. Well, we have minor changes here in the numerator here, which actually has R1 and R2 terms, where A is given by the term here, and rho that is shown here is an absolute value, and it models the correlation of the channel gain at t and t plus tau. And zeta is an incomplete gamma function here that's shown here. So here we show the steps to arrive at modified bivariate Nakagami M model for negative correlation case that we have shown in the previous slide, the steps involved in that. The first, before we start with the numerical observations here. So this plot on the right shows the level set contours plotted for a joint PDF of the channel gains at time t and t plus tau. These level set contours are concentric and share the same peak location, and the major axis here and here are perpendicular to each other. So using these numerical observations, we start with the joint PDF with GBU, the channel gains at t and t plus tau with the power correlation coefficient rho, and normalize the random variables y1 with the mean channel power at y1 and y2, and rotate the peak, rotate around the peak. The new variables that are defined are y1 tilde and y2. Actually, y2 tilde have a rotation, and then scale back to obtain the random variables, and then limit the support to make the PDF normalized to 1. Okay. So here we plot a power correlation coefficient, a model versus the measurements. Here the correlation coefficient rho t of t plus tau is plotted as a function of lag tau. Here we plot both analytical and also the empirical values for a setting of BUE is equal to 18 and BBS is 18, and the orientation change rate of 60 degrees per second. And we see these two match quite accurately, and this accurately models the SEM is what we show in this slide, the proposed model. And in this slide, we are showing the conditional CDF of the channel gain at time t plus tau, given the channel gain at time t is what we plot. On the left side, we actually show the case for power correlation being positive, and the right side we show it for the power correlation being negative. For the positive correlation case, the conditional CDF shows that for channel gain values g of t increasing, we see that the CDFs also move to the right. This indicates the positive correlation. And similarly, for the negative correlation case, as the GI of t increases from 0.6 to 1, the CDFs, the conditional CDFs actually move to the left, which shows that they actually are decreasing. And that corresponds to the negative correlation case. And in both these CDF plots that we are showing have a very good match over 3 orders of the magnitude in CDF and handles both positive and negative power correlation cases. Okay. So a quick recap of the problem that we discussed, where we have the pilot bursts which are periodically transmitted. Each pilot burst consists of the beams 1 to BBS transmitted on each of these symbols, and UE measures its received beam using one pilot burst at a time and cycles through its own received beams. At the last of the pilot burst in a measurement cycle, UE measures its a serving RX beam on it, and this measurement cycle has n data slots in it, and the pilot beam pair, so the beam pair that is chosen at this moment is used for the receiving the data in the next measurement cycle. There are S of the UE beams measured in each cycle. The optimization problem is to maximize the average data rate over n data slots and to find the beam selection rule that maximizes and finds the beam pair that maximizes the average data rate. That's an optimization problem of interest. So we show that the optimal rule by star of G is given by this. The beam pair B star U star that has the highest average data rate conditioned on its beam measurement is optimal. You observe that this function R is logarithmic, the rate is logarithmic, and it is difficult to find the term that needs to be maximized in a closed form expression. Okay. So to overcome this, we show a near optimal beam selection rule that uses the Jensen's inequality and the concavity of the rate function to come with this metric, where we show dBu of T of k is the metric of interest for us, which is easy to compute as we show in the next slide. The beam selection rule based on the upper bound that we discussed in the previous slide for the positively correlated case is given by this expression here. This is linear in omega and rho and the measurement that we have at for the beam BU. And for the negative correlation case is given by this expression. Okay. And if you note, for the positively correlated case, as the beam measurement increases, the selection metric also increases monotonically. Whereas for the negatively correlated case, as the beam measurement increases, the selection metric goes down. Okay. So here it indirectly is showing us direct relation between the beam gain and also the metric of interest for us. Okay. So once we have this metric, the beam pair that maximizes the average data rate based on the upper bound based selection rule is given by this expression summed over n data slots. As we observed, for rho greater than 0, the selection metric increases with the measurement, and for the rho less than 0 case, selection metric decreases with it, the beam measurement. The simulation results are shown with the same setup that we have discussed. Here I'm showing the illustration of the receive beam sequence for S is equal to 4 case. So for S is equal to 4 case, the beams that are measured are given here. We start with the beam measurement 1, the receive beam 1 and 2 and 3, and UQ star corresponds to the receive beam selected in the previous measurement cycle, and then 4, 5, 6 in the next measurement cycle. At the end of the measurement cycle, you choose the receive beam that was selected in the previous cycle, and in the next measurement cycle again 7, 8, 9, and the receive beam that was selected in the previous cycle. That's how it continues. Here you also observe that only a subset of S receive beams measured with a serving beam in each cycle, not all BUE beams. And the receive beam, the beam pair is selected at the end of each of the measurement cycle and reported. A quick flow diagram of the PABS rule that we just discussed is shown here. First, we receive the data with the selected receive beam over the n data slots during the measurement cycle from the previous measurement cycle, the selected receive beam from the previous measurement cycle. And during this measurement cycle, you measure the S beams in the sequential order as we have shown in the previous slide. And at the end of the measurement cycle, compute the PABS selection metric over the data duration using the angle of arrival and SCM parameters from the model. And select the receive beam for the data reception based on the selection rule given in the previous slides, and feedback the transmit beam to the base station. This slide shows the average rate as a function of orientation change rate. Average rate as a function of orientation change rate. The orientation change rate ranges from 0 to 120 degrees. 120 degrees of orientation change rate would correspond to rotating the device around in the hand within full 360 degrees in 3 seconds. That's a very large orientation change rate. Here we show the CPBS and PABS rules. CPBS rule is a conventional rule that ignores the time variation, selects the strongest beam pair, and the proposed rule uses the PABS selection rule that is shown in the previous slide. We show that the CPBS rule is grouped here for both S is equal to 6 and S is equal to 12 scenarios, and its performance, the average rate, decreases as the orientation change rate increases. Okay. For the PABS rule also, the average data rate reduces with the increasing data rate, while the average data rates are significantly higher compared to CPBS rule. And the PABS rules also reduce the rate mainly because of the reason that once you select a beam pair that is to be used for a measurement cycle, that is fixed during the measurement cycle. And even in that measurement cycle duration, the orientation still is changing because of the orientation change rates that we have. And hence, you see the beam pair that was selected at the start of the beam measurement cycle is not completely accurate and getting misaligned over the time, and hence this fall. Okay. And also you observe for S is equal to 6 versus S is equal to 12, there is the rate at which we are changing the beams is increasing. The rate at which we are changing the beams is increasing. Hence, we are actually using more accurate and more better aligned beams for S is equal to 6 compared to S is equal to 12 because of the long duration that is involved with the S is equal to 12. We also show here S is equal to 1 case, which is only measuring one of the measurement beams that doesn't is not possible in the measurement scheme that we have shown, where we at least S is equal to 2 is the minimum number of S that we need to show. And with that, we actually don't have degradation going on here. We observe that the PA-based rule, we also plotted the Gini-aided rule for all S is equal to 1, S is equal to 6 and 12 cases here. Our PA-based rule is very close to the Gini-aided rule for all these cases. All these cases, S is equal to 6 and S is equal to 12. And it's near optimal is what we claim in this slide. The role of number of beams measured per measurement cycle is shown in this. We plot average rate as a function of the peak SNR for multiple values of S is equal to 6, S is equal to 12 and S is equal to 18 are plotted in this. We see that the average rate at each of these SNR points reduces for S is equal to 6, 12 and 18. Okay. So S is equal to 18 would correspond to the case where all the beams are measured before you choose the next beam pair, whereas S is equal to 6 corresponds to you measure only a subset of 6 beams before you select a beam, and this reduces the time over which the misaligned beam is used consecutively over the for receiving data. Okay. The longer measurement cycle delays the beam selection occasion and resulting in a suboptimal beam being used for a longer time. Okay. So further, we asked two new questions. Okay. In the previous work that I have shown you, we were measuring the received beams in a sequential order and a round robin fashion. But is that the right thing to do? Okay, which instead of that, which subset can we measure? And also we assumed AOA is available at the UE, and if it is not available, how do we even estimate it? And these are the two main questions we ask in the following part of the work here. The current status of the solutions considers beams as arms, and mostly the stationary environment is assumed, and limited consideration of the practical sounding schemes are assumed. There is no prior work on the joint AOA and beam selection in the literature as of now. Okay. The core idea of applying latent Thompson sampling is to model AOA as a latent state variable that is invariant to UE orientation changes. Okay. The measurement model and system model remains exactly same as what we have seen in the previous slides at the start of the presentation, but with a minor change in the way we select the beams for measurement. Here, of the S beams that can be measured in one measurement cycle, we select the beams that are to be measured in each measurement cycle at the end of the previous cycle. So here we are placing a square bracket around each of these number here, which represents the first beam that is measured in this measurement cycle and S-1th beam that is measured in this measurement cycle. And in every measurement cycle, we continue to measure the serving receive beam on the last measurement occasion. And this is compliant to 5G sounding procedures. And measurement sequence is measures the shortlisted 1 to S-1 in square brackets instead of the round robin fashion that we have followed till now. Quick overview through a flowchart. There are two things that are happening in this work, in this part of the algorithm, right? One is to select the measurement subset selection, the beams to be measured, and also the data beam pair selection. Okay, so let's see the first beam measurement subset selection. Measure the beam pairs gains of all BS transmit beams using the selected RUE receive beams. Let's assume there is some subset of RUE beams available. So using these beams, we update the prior corresponding to the theta, the AOA, and sample the AOA distribution to get AOA estimate And using that, you select the receive beam subset for the measurements. Using the same AOA, we predict the beam pair gains over the data duration using the AOA that's available here. And then using that, we select the receive beam for the data reception and use the selected beam for transmit beam for reporting to the base station, and at the receiver you use the receive beam as is. The steps involve the obtaining the measurements and computing the rewards, and updating the AOA pairs and sampling a new AOA, and predicting the data beam pair and feedback transmit beam. And then action is to select the beam subset for the next measurement cycle at the end of each measurement cycle. So the latent Thompson sampling setup is shown in this slide. Here we have action, context, and the latent spaces. The action is a sequence of beams to be measured, is an action that we have in this form, where the S-1 beams are selected and the last beam is selected as the receive beam. The context is the sequence of user orientation changes up to the Qth cycle. We assume that this is available because of the sensors availability on the user equipment. The latent space D and the state. The possible AOAs of the LOH paths at the UE are quantized into D options around the UE, and they're formed as a latent space, and then D such options are possible for us to choose from. We first start with a simpler rule. It is called LTBS BB, the latent Thompson beam selection, using the beta Bernoulli prior is what we actually show here. The reward here is Bernoulli and the AOA prior is beta distributed. The reward is given by R, which is equal to 1 if the beam power measured is greater than a threshold, otherwise it is 0. It is quite simple to calculate as soon as we have the measurement. The prior update for this case, the beta Bernoulli case, is done by using this formula, the beta parameters of AOA, wherein AOA is our latent state. The theta state beta parameters are updated by the reward obtained here, alpha d, with a simple addition parameters. It's very easy to update the priors. The action for this case, the LTBS BB, is selected as follows. You sample the beta distribution of all the directions in the AOA states, and once you have the sampled variable, choose the direction which has the maximum sampled value, and that direction, the phi d tilde that corresponds to d tilde, is the chosen AOA. Once you have the chosen AOA, you compute the expected reward corresponding to that, which is given by this function. And choose the beams with the largest expected reward given phi tilde and the context till now, that is orientation changes till now. And these are the beams that will be used to measure in the next measurement cycle. Now we show LTBS SCM is latent Thompson sampling based beam selection that depends on the SCM channel model that we have discussed in the previous slides. Here the reward is the maximum of the channel beam measurement power and a threshold, which is the signal strength here. Here you observe this has more resolution. That means it represents the actual channel power instead of 0 or 1 as we saw in the previous slide for the LTBS BB case. Okay. The prior update for this is done using the base rule, which are given by the expressions here. So if you observe this, these are computationally more involved. Unlike the previous one, it was just a sum or a subtraction, addition or subtraction of the reward. And these are, while these are very computationally involved, this is realistic reward and prior update. So for selecting action, we first sample the prior. You first draw a sample from the multinomial PDF with the PQ and choose D tilde, which picks one of those PQ options that we have. And use that D tilde to choose the DOA state. It's just a sampling the pair that we have, which is a multinomial polynomial. Once the AOA is chosen, you find the action which maximizes the expected reward. Expected reward is given by this expression, which is a closed form expression, and it can be computed, and the UE chooses the beams with the largest expected reward given the AOA and the UE orientation changes. Next is a data beam selection. So data beam selection metric is from before is shown here, given the phi q tilde, that is selected AOA. While the expression remains same, we now release the assumption that AOA is known. Instead, we actually use the AOA that is estimated or sampled in the previous steps. And we select the data beam in such a way that maximizes the average selection metric over the next n data slots, and that beam pair is chosen for receiving the data in the next measurement cycle. So we also do regret analysis for both LTBS SCM and LTBS BB, and they depend on LTBS SCM, it depends on the tau parameter, the threshold parameter that we have, and LTBS BB doesn't depend on it. Okay, we show the simulation results with the simulation parameters shown in this table. The left side parameters show the TXRX parameters correspond to number of beams at the BS and UE, number of transmit and receive antennas, center frequency, the separation between the antennas, slot duration, pallet duration, bus periodicity, and the SCM parameters on the right side corresponding to the SCM that's chosen in the simulation setup, the Riccian factor, the clusters, the number of pass flow clusters, mean AOA and AOD, and UV speed considered in this slide. Simulation results. Here, we first would like to highlight the angular of arrival tracking that is used in this LTBS methods. Here we show the angular of arrival estimate as a function of the cycle index Q. Okay, each simulation runs for these number of cycles, and we see that LTBS BB, here we plot LTBS BB, LTBS SCM, and actual AOA. Actual AOA is set at 60 degrees, 60 degrees. Okay, you see that LTBS BB and LTBS SCM actually track this reasonably well, closely, while LTBS SCM is very close to the actual value. Okay, this is at the while the orientation of the device is still changing. That is this is the estimate that we have for a value of S is equal to 6. So you see that we have accurate AOA estimation. So LTBS SCM mean error is close to 0, it's minus 0.03 degrees, while the standard deviation is less than half degree. And LTBS BB mean error is minus 3.3 degrees, and the standard deviation is around 28 degrees. Also, LTBS BB takes more time to settle, whereas LTBS SCM settles in 3 to 4 measurement cycles. Okay. On this slide, we plot measurement exploitation as a function of the orientation change rate. So measurement exploitation is the probability that the best beam is among the chosen S received beams for measurement. Okay, this actually confirms that if that is measured, you would actually get a chance to select it as well. So we actually consider that as a measurement exploitation probability. Here, here we plot the measurement exploitation probability for gene-aided method, for which the exploitation probability is always 1, and the LTBS SCM method and LTBS BB, and method with randomly selecting the beams over the time, and the round robin fashion, and then TBS, the Thompson beam sampling, where the beam selection, the Thompson sampling selects the arms, beams as arms directly, not in the latent space. And UCB and epsilon greedy methods are used to compare the proposed methods. Okay. Here we have plotted this for S is equal to 6 and the peak SNR of 20 dB. Okay. And we see that the LTBS SEM is quite close to 1. It's about around 98% and above exploitation probability. While LTBS BB, which is quite close to LTBS SEM, but it is around 90%, 95% and above. While the all other methods, the random beam selection, the RR, the round robin, TBS, UCB, and epsilon greedy, continuously decrease in measurement exploitation probability with increasing orientation change rate, because they are unable to track the ongoing changes and find the right set of beams that are to be measured in the next measurement cycle, because they, and it shows a high measurement exploitation probability for the proposed schemes. On this plot, we show the average rate as a function of the orientation change rate. This corresponds to the simulation that we have shown in the previous slide, where we have shown the exploitation probability. You can link the exploitation probability to the average rate. Here we have plotted Gini, which actually knows what is the right beam to be used, right beam pair to be used in the next measurement cycle accurately all the time. We have LTBS SEM and LTBS BB and R&D, random, round robin, TBS, UCB, and epsilon greedy, as we shown in the previous slide. We see that LTBS SEM is quite close, within 1% of the Gini aided method, while LTBS BB is below the Gini and quite close to it. Not too close actually. So we explain the reason for it. The reason for this degradation is because of the missing exploitation probability resulting in OA misselection in some of the occasions, resulting in a cascaded error in the beam selected on average. Okay, we observe the average data rate for all other methods significantly degrades with the increasing orientation change rate. While LTBS SEM is close to Gini aided method, LTBS BB with simplistic beta pair does 50% better than the other methods, while still is worse than the known the LTBS SEM method. The other methods average rates reduce significantly. Effect of the latent space size D. As we have shown in the previous slides, the latent space is divided into D discrete states, and as we change the AOA state space from 0 to a large number, how would the average data rate change is what we show in this slide. Okay, so we have plotted Gini. Gini doesn't have this effect because it already knows what's the right thing to do, so it is consistently at the same value over all D sizes. The LTBS SEM and LTBS BB have these latent states involved in their implementation, so they are both these methods are plotted in this. We see that LTBS SEM starts with a lower value of average rate and consistently improves as the AOA space increases, space size increases, and saturates after some time and reaches close to Gini value. Whereas LTBS BB method starts and increases after 180 degrees. They are kind of both LTBS SEM and LTBS BB settle down and no further improvement after that. And you observe that I would like you to observe a couple of things here. The LTBS BB saturates a little bit earlier than LTBS BB. This is mainly because of the errors that we have shown. Okay, LTBS BB itself actually introduces its own estimation errors in AOA as we have discussed in the previous slides here. So even if AOA estimation would increase, or the number of states increase, reducing the resolution between them, increasing the resolution between them, it doesn't help the method because there is inherent error that is coming in because of the inaccurate model that it uses for updating the prayers. Okay, and hence it actually saturates a little earlier. Okay, this doesn't need more than let's say 75 AOA states space size, while the LTBS SCM needs more states because it has the capability to estimate more accurately because of the inherent accurate model that it uses for updating the prayer and obtaining the rewards. Okay, so D greater than 180 is sufficient for both the cases together, is what our finding is. Later, we extend the Thompson sampling work to lateral mobility. So, lateral mobility, in the lateral mobility, user device moves from one location to other, resulting in angular of arrival changes at the user. So, this will need, that would actually mean the prayers that we have obtained or the prayer updates that we have done in the previous measurement occasions with the set AOA is not relevant at the new location. Okay, to overcome this problem, we actually use windowed prayer updates, wherein you use past W measurements to update the prayer. That means you have at measurement cycle Q, you use only the W measurements in the past to update your prayers and use them for further updating the AOA. This actually helps us finding, ignoring the measurements which are obtained with the older AOA assumptions, and hence improving the accuracy of AOA with the windowed approach. Okay. Let's show how this windowed updates happen. The time varying LTBS BB, that is beta Bernoulli based one, still remains simple with additions and subtractions with windowing there. You just sum the rewards that you have only over the last W cycles, while LTBS SCM also uses the windowed prayer, but here the expression is still involved. We use only at every measurement cycle we use the past W and we recompute the prayers corresponding to that. Okay, so use past W rewards are used to update the prayers and for both the cases with the expressions given in this slide. On this slide, we show the lateral mobility and AOE estimation and tracking scenario here. Okay. We show the AOE estimate as a function of the cycle index. Here, for the TV LTBS SCM method, that means the two new methods that we have adopted for lateral mobility, and also for the older methods that we used in the LTBS SCM and LTBS BB, which were not adapted for the time varying nature. And we also plot the actual value. Here you see, as we said, with the lateral mobility, we have AOA changing over the time over the measurement cycles. Okay, here we have assumed AOA change rate of 10 degrees per second, which would correspond to approximately 120 kilometer speed at a distance of 200 meters, which is quite large. Here we see that the TV, let's first see the older methods, LTBS SCM and LTBS BB methods actually are unable to track the AOA accurately. You see the LTBS BB here, it actually deviates quite far away from and quite laggy. And also LTBS SCM is also stuck at some point and then is unable to really track it, and it actually at some moment gets back to the actual AOA and then once again stuck at a particular same estimate. This is because it is using the older values, older measurements which correspond to this AOA. It's stuck here. It needs some momentum. It's time for it to really once again go back to the normal. It's actually quite far away from the actual measurements. Whereas TV LTBS BB is quite close to it with a few jumps here, and TV LTBS SCM is quite close to the blue curve, which is close on top of the actual value or close to actual value. Okay. It's quite robust to lateral mobility. The TV LTBS SCM and time varying LTBS BB, both methods are quite robust to lateral mobility. Here we show the mean error for the SCM case is only 1.82 degrees, and the standard deviation is only 1.38 degrees. For the LTBS BB time variant version, we have mean error to be around 2.26 degrees and the standard deviation is around 29 degrees. For the same same scenario with the same setup, we actually plot now average rate as a function of the AOA change rate. So AOA change rate of 10 degrees would correspond to approximately 120 kilometers per hour at a distance of 200 meters. Here we see we have plotted Gini edit and the TV-LTBS SCM and TV-LTBS BB methods and other benchmarking methods here. We see that the TV-LTBS SCM is doing quite better than the bunch of the benchmarking methods, and even the TV-LTBS BB also is doing quite good compared to other benchmarking methods. So we show these methods are robust to lateral mobility, where the lateral mobility with AOA change rates is all other methods actually floor up to 3 bits per second per hertz. This is a summary. We have first shown and proposed a modified bivariate Nakagami M model for SCM. This addresses the non-linearity of the channel, so non-stationarity of the channel, and handle the positively and negatively correlated scenarios in SCM, and is also model usable for other use cases like channel estimation, which can use the correlation across time to get a better estimate. And further, later we actually proposed orientation aware beam selection rule that is simple affine form and is near optimal and outperforms the conventional power-based beam selection rules. Later, we released the assumptions that we made in this part of the work and removed the assumption that AOA is available, and then come up with a latent Thompson sampling which does a joint AOA and beam selection rule. It uses AOA as a latent state and combines the beam subset selection, AOA tracking, and data beam selection into one method, and extension to time varying AOA is also shown. Here are the list of publications. The first two publications are in transactions and wireless communications, and the third one is in Globecom 2021, and we have 2 patents, and one of them is granted, other is in process. Thank you. Thank you for listening in today.